best way to start this kind of talk will be just to quote the reason why we are here, because it's the 100th anniversary of the Darcy-Thompson growth and form. And actually we owe him this idea that mechanics plays a role in the formation of a shape. And especially, I made it disappear. He actually quotes in the introduction. It's a beautiful book. I would really advise at least to have a look very quickly, because it's more than 1,000 pages, and it has like the spirit of collectioning. So it really was a careful, like naturalist. He went to look at nature. He collected a lot of thousands of different species, and he studied them. But I think this quote in the introduction is very important, because it says at one point that we have to start a mechanical philosophy about morphogenesis. And just quoting the Principia of Newton, it says that just nature is pleased with simplicity. There is no superficial stuff there. And especially there is this way that actually nature finds use for everything. And finding use for everything means that somehow there is an adaptation. So what you become, maybe you're not the best of your human being that you are, but you know that at least nature tends you to become the best of possible things. So you are built with a function, and you tend to be as efficient as you can in that function. And if you think about it today, it seems like, okay, it seems like a well-acquainted way of investigating that from a scientific viewpoint. But you have to understand that at that point it was kind of a revolutionary concept, because 100 years before him, there were still scientific papers published like investigating the possible idea that you could find a miniature man inside a sperm cell. So people really still believe that there was no such kind of mechanical adaptation. There was already something programmed in it. So in that sense, Darcy-Thompson was a pioneer. And in his view, his view of morphogenesis was just like a static view, in the sense that he imagined that forces shape. How do they shape? It's just like imagine that you have whatever material who has an internal energy, and it is subjected to a force outside. So you actually have to minimize this function, which is the internal energy plus the work done by external energy. So you find actually, you went studying the shapes of fish, for example, at different depths, and see that they were subjected to different force, they get different shapes, just a static minimization. But then we had to wait till Turing to make this picture become a little bit dynamic. And Turing actually, it's one of maybe really the very first case in which a mathematician helped biologists to develop a theory. In my viewpoint now will be the reverse in the next year. There will be biologists that will give us mathematicians new problems. But actually, Turing got the idea that there was some dynamic, because size and shape is about scaling. It's about finding a length scale. It's about organizing at a different scales. So this could be done, for example, by using reaction diffusion equations. So he actually had the idea that there were some kind of, let's say, particles. He didn't actually imagine what they were. They called that morphogens. There were some kind of diffusing molecules inside the material, and these diffusing molecules could actually help giving a double function. And the double function was on one side to give information about positioning. So they give the scaling, length scale. And on the other side, they were somehow a signal for growth. So in one sense, they will do the two things at the same time. They make the material growth, and they tell him how to grow. So they give information about his position. And later on, actually, morphogens has been identified in the biological world only a few decades after. So in that sense, Turing was a pioneer. And you actually can have all these kind of intricate patterns by actually making these morphogens somehow interact with them. But then again, let's go and read the original paper of Turing. And if you go and read the original paper of Turing, in the introduction itself, he makes a very precise statement. And it says, well, it's a hell of a problem. And the hell of the problem is because if you want to really model this as accurate as you can, you should take into account changes of position and velocity by Newton's law, stresses given by elasticity. So actually, it's actually a quote about elasticity in Turing's papers. The chemical reaction and the diffusion of chemical substances. Then the assumption is done that problem has many features, a lot of electrical problems and internal structure, but it's a problem of formidable mathematical complexity. So what Turing does, and only great people can do that, to just use a simple model, but you get a very, very complicated and useful results. Turing say, okay, I just focus on chemistry, and I just show that even if just considering that these diffusion are very different from one from each other, I can have very, very complicated shapes. So he just got a subclass of this problem, and they found a beautiful, beautiful result. In a, of course, much more humble way, what I'm trying to do now is to show that actually the biological advancement that come, we have a lot of new data. We know more both about the elastic behavior of the material and especially about the biological world, what happens at these lower scales. So actually we can try now to follow this initial Turing's idea and see how we can match this chemical and mechanical world together to see what happens in shape. So from a modeler point of view, we have a very peculiar system, in the sense that if we are used with inert matter, we know that if we put a scale like elastic modulus and length scale, all inert matter that we know stay on the up right corner of this diagram. But if we look at biological materials, we have matter which is low length scales, but very compliant as well. So actually, we have to refine our tools in order to model that. And at the same site, it's an intrinsically multi-scale problem, because it's inside the cells there are filament cells attached to make tissues that make organs. So if you want really to take that into account, you have to upscale these properties into microscopic properties into macroscopic properties. And every time you do a step in that, you have to change your lens in which you observe your problem. You have to change your mathematical tool. So it's an intrinsically fascinating problem on that viewpoint. So you actually end up with a very nonlinear problem. Which kind of nonlinearities we have inside this? Well, we have the fact that we are dealing with compliant matters, and compliant with even some kind of strange rheology. If you take a cell now that duplicates, at some time scales it behaves like a solid, at some time scales it behaves like a fluid. So it's a very nonlinear constitutive behavior. So there is a material nonlinearities, but at the same time there is a lot. If you imagine from an embryo to an adult form, it makes a great deformation, a great shape. So there is a geometric nonlinearity in that. This means that we end up solving coupled nonlinear PDEs, which is very fascinating, but not so trivial to find any kind of solution. And if you are dealing with shape, it means that if you have a very nonlinear problem, you end up having a lot of solutions. So we end up a lot of possible transition and multiple bifurcation between one and the other solution. And this is the key of some part of what I will show you today. On the other side, there is a size effect. And I think this is a beautiful thing that all students should have when an introduction about how to model biological systems. I took this from an article of Physics Today by Phillips and Quake. And I think it's very useful because it just makes a very simple calculation in text. Okay, thermal energy is about kBT. So 10 minus 20 joules. Let's now calculate what is the energy of bending a rod of aspect ratio 20:1. So it makes energy over length. And this is the curve that we have. What is the energy of fracturing such a rod? And we have the green curve. What is the energy on electrostatic shell, a spherical shell, bind them together, and which is the energy of the binding energy of an electron in a box. You plot all them all, and what you find is that there is a length scale where all these energies have the same magnitude. These length scales are of the order of the nanometer, but what does it mean? That at this crossover length, there is a bunch of opportunities, because at these length scales, you can build some system in which you can exchange a chemical energy into a mechanical energy. You can exchange an electrostatic energy in any kind of other energy. So actually, that is why our life it builds at these scales, because at these scales, all these energy are the same, and you can actually transfer optimally one kind of energy into another kind of energy. And that's a very important point. So what's now a little bit more modern feature of morphogenetic events? I find this very illustrative. It's a review of Lequy and Legoff who came out in Nature about 10 years ago. So imagine now that you start your life as a bunch of cells. It's here. And these cells are random proliferation rates. At one point, the picture can get complicated in the sense that there is some chemical diffusing. This gives a polarization of this growth, and growth can actually reorient in some preferred direction. At one point, cells differentiate. And by differentiated, they enter into competition. So you started from a bunch of cells, a single species, and you actually have some kind of different species kind of competing one to each other. At that point, well, they have to create a structure, so they need to change relative position between each other. By changing relative position, they do a material rearrangement. So they try to find their optimal microstructure. And then they are subjected, for example, to morphogens, so diffusing chemicals. And these diffusing chemicals act both as local positioners and as growth factors. So they create some kind of localized growth where the gradient is in between center cell threshold, like, for example, in the French flag model. But creating growth actually is not always compatible with the constraints that the material has. So you have a growth in the inner core, for example. The material is somehow compressed by the outer matter that it has. So this creates a mechanical, for example, compression. And this has been pointed out that the mechanical compression, for example, is an inhibitor for growth. So inhibiting growth means that the growth rate diminishes. So conversely, chemical feedback changes the distribution of morphogen, and it starts somehow a feedback loop. So this feedback loop changes the chemical and changes the growth of this material. So it all have to end up into a steady state, and this steady state is where the material reaches its final shape, its final function, is well organized. So it is kind of a steady state solution of coupled nonlinear differential equation where it magically ends up with the fact that you have a hand with 5 fingers with a given size. So there is something programmed inside, but it's really a very fascinating problem to get solved. So at the beginning, I will just show you a little bit of some, in a more qualitative way, some examples of this coupling between chemical and mechanical energy. And then I will just try to work a little bit more detail a problem in living matter, which is the formation of residual stress due to growth. So the first problem that I would like to just highlight in here is how we regulate the size and the shape of an organism. And in order to do that, I have to take the simplest system model that I can get access to. And this simplest system model is the imaginal wing of the fruit fly, the Drosophila. So the imaginal wing is a bunch of embryonic cells. It has something even less than 100 microns at the beginning, that in the adult form will become the wing of this fruit fly. Biologists love it because it's practically bidimensional. It has no flat. And it has a very striking feature that if you observe it over time, some 48, 2, 3, 4 days, you see that actually the deformation that it gets through is just affine. The same shape, but it's like you have a scalable vector and you just magnify it. And even more astonishingly, if you go and have a zoom at the microstructure on how cells are distributed in here, the cells keep their relative positioning. So the blue cells is always there, and in between the blue cells and the pink cells, there is always the same number of cells. So it's kind of stretching out. Where's the problem in this? It's just that how does growth comes out? It comes out because in the middle of the wave, which is of the wing, which is this dark green line, there is a source of this morphogen, and this morphogen is called DTP. The morphogen is just produced there, and then it decays and absorbed from the other cells. So what people actually do experimentally, just to go and look through fluorescence imaging and look at which is the concentration of the morphogen in these different stages of the development. And what they find is just that if you plot all the concentration curves and you scale them with a dimensionless variable, which is the relative position, so position over the length of the domain, and the length of the domain changes, they found that all these curves, they actually collapse into a single curve. And this is something that, from a physicist viewpoint, it's very puzzling, because the reaction diffusion is a mechanism that microscopically, the diffusion is just Brownian motion. So I don't expect that the diffusion coefficient changes in this kind of material, because the cells are at the same size, they just reproduce, but there is no, they don't change with the length of the domain. So that equation, it gives a line scale, which is the square root of d over the absorption coefficient, but these coefficients, these material parameters, they don't depend on the domain. So how is that possible to coordinate a growth like that? So we came out, actually, with Davide, we actually got interested into this problem. It was very difficult to get in touch with biologists over this, but we just read it carefully about literature, because we had an idea in mind, and we wanted to see if this idea was somehow viable. And first of all, we have a problem, and the problem is that, well, we have to break the symmetry, because there is a mirror symmetry on the vertical axis, but this grows somehow, it scales from some point. So we have to have some other field that somehow creates a different symmetry. We want to have a point symmetry, and we actually found that there is another actually morphogen in this system, which is called the wingless, which is secreted in this red line, which is exactly orthogonal to the other line that we had seen for the other morphogen, the DTP. And this wingless morphogen is correlated to some kind of directional growth of the cells, which means that it's correlated to the expression of a myosin, which is DAX, and so it's been said that locally cells can read this information and they can adapt the direction of their growth comparing of the intensity of this. So the two morphogens together, they create a radial symmetry. Inside a given ratio, they can actually orient cells, so they can actually create some kind of active deformation in the central pouch of this. So by doing so, we actually ended up, are we able to create some kind of scale invariant solution of this? And actually we realized that stress can do that. Because if you imagine that there is this wing, and at the center of this wing there is a compression given by the fact that they read the two information of the morphogens, so they kind of use this myosin to contract it, then the outer materials is somehow contracted. But how does the stress scales? Actually, what we found is that the stress just scales in a way that is exactly what we need. So it's something whose intensity depends on the domain, but whose special variation is exactly something that depends on the relative solution. So this actually somehow gives an information. So we did some kind of we did the analytical part in some kind of very convenient choice of symmetries, but then we just made numerical simulation of finite elements, and we have seen actually we could compare our results with what the people found using photoelasticity, which means that people can take this wing, can get some kind of light diffraction, and by light diffraction they measure the difference in between the two principal directions, so they find kind of anisotropy. And actually the results are in qualitative agreement. So actually that's a good candidate. I'm not saying that this solves the problem, but it gives you another idea about in this problem, which is that actually cells can use this mechanical stress to be a local controller of a global shape. So the mechanical, the elastic boundary value problem gives the information about the domain, and cells can read the local information and have access to what is the global shape of the material. Another problem related to the influence of mechanical and chemical cues on morphogenesis is given simply by the effect of stress, mechanical stress on the growth. And there has been a seminal experiment made 20 years ago by the group of Rakesh Jain at MIT. They just took a bunch of cells, of tumor cells, which under some confluence condition they end up doing a spheroid, and they embedded them in some kind of gel. It's a magic component called matrigel that no one knows what's inside, but it's kind of a porous material full of water and some kind of fibers. And then they made the spheroid grow because it is permeable to glucose or some kind of nutrients for the tumor. It grows, but it cannot grow because actually on the other side the porous media exert a compression, and depending on this compression, actually, they found that after the first exponential growth of the growth law, they found a linear phase and then a saturation. So there is actually a threshold, a pressure that can make this growth saturate. And especially the more one increases the pressure, the easier and the sooner it saturates this growth pressure. So recently at Institute Curie, they redid this kind of experiment in a, let's say, experimentally smarter way, which is the effect now to reproduce the effect of a mechanical compression by a constant pressure. And they did that by just taking the same spheroid, but adding in the solution a big molecule, which is the dextran. And this dextran is very big, so it creates an osmotic pressure. It's bigger than the tumor interstitial pore size. So it exerts an osmotic pressure on the outside that can be easily controlled just by its local concentration in the bath. So they did the same stuff, and they found the same type of kind of behavior. So, but this time they had a clear-cut indication which is the inhibiting pressure and which is the effect by changing this inhibiting pressure. Then people ask themselves, but is that a problem that I'm just a fluid problem, I'm interested in hydrostatic pressure, or is it something related to forces? Because if it is a solid-like phenomenon, it has to depend on something which is not isotropic. So they're actually trying to exert this kind of compression in an anisotropic way. And this was an experiment made by the group of Chang and others. They just embedded again in this kind of gel, but at this point they added two beds on the sides. And by adding these beds, when they compress, these beds create a fracture. So fracture release tension in one direction. So actually they ended up from having a spheroid, round spheroid, to having an oblate spheroid. Then they added some kind of fluorescent molecule to detect how was distributed the proliferation and apoptotic rate, and they found out that the distribution of the mitotic rate actually correlated exactly with the distribution of stress inside it. So there is actually something at the level of subcellular level that transforms the mechanical signal into the chemical signal. Our idea of modeling this kind of phenomenon was the fact that actually we are dealing with a material which is the tumor cells, which is a mix between solid part, which are the cell, and water. So imagine like you have a sponge, a solid sponge full of water. If you take this solid sponge and you put it at the bottom of the ocean, the sponge doesn't deform because the pressure of the ocean, it gets taken by the liquid component. So it doesn't take the pressure outside. But if instead of putting that into the ocean, you just take big spheres which are bigger than the pores of the sponge, they exert a pressure which is taken only on the solid component and not on the liquid component. So we have this kind of modeling where the solid component can also grow. And what does it mean grow in this model? I will come back later on this. It's just that it changes the metric of the elastic deformation, which means that by growing, the deformation has a reference configuration which is changes. So by adding this growth, I change the deformation in which the material is subjected. On the other side, I have a chemical component that diffuses. This is the classical Greenspan model for tumors, so a classical reaction diffusion modeling. And I have to couple them. So I have to couple the growth, and I have to couple the chemical and the mechanical stress. So what we end up doing is just that by actually creating a simple chemo-mechanical feedback on this, we could reproduce this kind of behavior. So it's something that the growth, it depends on the local concentration of the nutrient, but it also has an inhibiting effect depending on an invariant, a proper invariant measure of the stress inside this material. So This is transmitted at the subcellular level by some kind of transmembrane proteins, which are integrins or cadenins, which are able to give a local information to the cells on what is the deformation that the outer material has. Okay. The result of this was the fact that actually we reproduce this growth law that depends on the pressure. So this is the blue one is the free growth law. The other materials are how we add the pressure of the osmotic pressure, and you have this some kind of inhibiting effect. But we also reproduce another effect, and this other effect is that by creating a growth which is dependent on the stress is locally inhomogeneous, so the growth is homogeneous. And being inhomogeneous, it creates a region inside that wants to grow more than the region outside. So overall, they have to accommodate this misfit. And by accommodating this misfit, they create some kind of residual stress. So we actually found a distribution of residual stress inside. How do you see that in the physical world? Well, if you want to see a residual stress, you have to cut, for example. I will see if I have time. I'll show you that you don't really have to do that, but that's what we did. Our good collaborators, Triantafyllos Stylianopoulos, made this, took some tumor, implanted some tumor in mice, then they took them out, and then they cut. They just made a radial cut on it. And what we found is just that it opens up. But it opens up in a weird way. It means that in the outer part, it tends to open up. In the inner part, it tends to overlap. It goes to self-contact. What does it mean? It means that in the outer part, normally, it is in circumferential tension, while in the inner part, it is in compression. And this is exactly something which is reproduced by this kind of model. And then we just did some numerical simulation out of our results, and we find a very good qualitative agreement out of this. Another idea of how mechanics is important in biological problems is the idea that actually sometimes mechanical instabilities are used to create pre-patterning. And this is a very important point. For example, imagine that you are an endoscopist and you put your endoscope in the throat of your patient and you look at what you find in the mucosal of the gastrointestinal tract. You enter from the esophagus, and you find this kind of circumferential wrinkles. Then you go down in the intestine, and you find that actually you find this kind of biaxial wrinkles that end up like being the villi in the intestines. You go down in the jejunum, and you find this kind of wrinkles in the longitudinal ways. And the question was like, how can this tissue that differentiate at the same stage of development from the same kind of original embryonic tissue can give rise to this kind of patterns? And because actually what we actually found out is just you already have this kind of patterns 2 weeks after you are fertilized as an embryo. So it's actually one of the oldest things you have in your body done. And our idea is just that since it's coming from the fact that we have 2 layers, and they are the embryonic mesoderm and the embryonic mesoderm, that they kind of grow in a different way. So actually the fact that you develop one pattern compared to the other is just a mechanical instability. And this mechanical instability is just purely dominated by geometric and material properties. Geometric, which is the length scale, which is the ratio between the thickness of these pre-embryonic these embryonic tissues, and material, which is the relationship between the thickness of this. And you constructed the phase diagram, and we can actually have all this kind of behavior in the same stuff. So it's actually a mechanical pre-patterning. And as I was telling before, it's a nonlinear, very nonlinear problem. So I don't expect this to be a solution which is stable in the long run, because as long as you keep on growing, it can create secondary bifurcation, tertiary bifurcation, period doubling. You can have formation of folds. So it's a very rich mechanical model. But what is essential here to remember is that actually biology builds on this. Its biology uses this mechanical instability to give a message to the cell. Once you have a mechanical instability, once you feel that your local curvature has changed, you activate another kind of biological process, and this kind of biological process differentiates your cells. So in the intestine, they feel there is a Gaussian curvature, and they activate the differentiation in villi, which is not done in the intestine because there is no Gaussian curvature in the stomach, for example. Another idea of mechanical instability, it ended up when we studied a little bit how do tumors somehow survive the fact that at one point getting food by simple diffusion is no longer enough. And it's no longer enough because at one point they create an internal intravascular pressure which is too big. So whatever comes from the outside actually bounces back. It's not able to penetrate in the tumor. So the tumor will be in that phase, which is the avascular phase, will have a destiny to fail, to die. So in order to, when it does that, what happens in that instead? It happens that when it becomes suffering that much, it creates some kind of toxic waves that promotes the secretion of a molecule, which is a vascular endothelial growth factor. Which means that tumor at one point sends out a message for help. This message for help reaches a capillary which is somehow a few millimeters away from him and tells him, please grow in my direction and reach me and bring me some blood, because otherwise I will be destined to die. But what we finally, and if we study the vasculature that the tumor constructs around itself, it's very different from the vasculature that we have in the healthy tissue. But it's different because it has been done in a different way and in a different environment. It's not something that we end up from doing from our embryonic life, but we do from our adult life. So the boundary, the surrounding matter is different from what we have. And somehow, from a physicist point of view, it reminds a little bit of the problem of supercooling. It's some very irregular, which is some kind of branching here and there. So we actually try to study it as a chemo-mechanical instability. It's another hypothesis. There is a lot of work on angiogenesis. There is a lot of chemical signaling in it, inhibiting. There is this salt and pepper pattern. There is a lot of complexity in the chemical world, but we just end up with a simple chemical model, which is there is something, a nutrient that diffuses, it is absorbed at one point, and it creates actually, if you look at this number, diffusion and the sink term, it creates a very, very narrow transition zone, which means that growth is localized really in a very narrow zone, which is at the boundary of the capillary layer. And then actually we can kind of homogenize this narrow zone and treat it like a moving material interface, like we do with supercooling, for example. So we have some kind of Rankine-Hugoniot condition that move this material interface, and which are sensitive to the energy jump that we have from the chemistry, and on the other side is sensitive to another important point, which is curvature, and which is something that in supercooling, for example, we know by Gibbs-Thompson law. Yeah, there is a capillary effect given by the fact that there is a curved boundary. It has more or less energy compared to a straight boundary. So what we do is just implemented this kind of let's see if it goes, of modeling in simulations, which should at one point run. So what happens is tumor sends the signal. There is one point of the capillary wall that gets a high enough concentration to start secreting material, and then it starts trying to reach out the tumor. And by reaching out the tumors, two important things happen. And the two important things that happen is just that the branches increase their velocity by approaching the tumor, which is something that is observed in the real world. And on the other side, there is the fact that the branching frequency becomes higher as well, because this is an instability which is very catastrophic in that sense as well. So there is a kind of a fractal structure. It's not so easy to understand how this correlates actually, how the structure correlates with the mechanical parameters, but it is a qualitative different way of expressing this kind of behavior in tumors. So since it seems I ran out of time, I just jump to the conclusion, I've been going to the core of what I was saying, but I think that I'm always an optimist. I always was even trying to find a way that I could jump into and walk myself as well into the desk, but I couldn't find an example where it allowed me to do it. So I left to find like all good literary people in the medieval times did. So I end up with a circular talk. So I end up with the point where I started. And the point where I started was Darcy Thompson. And again, it's Darcy Thompson's introduction. But at this point, it's just a quoting that Darcy Thompson put in his book before writing it. And especially, there were these two things that I found particularly brilliant. The first, it was a quotation of Sir Herschel. Sir Herschel was the most conservative scientist and was like kind of the baron of embryologists in the 19th century. He was completely opposed to any kind of mechanical view. He was really a preformationist, and he made the war of all these people who tried to put some kind of mechanical ideas. And Herschel actually said very kindly that natural history is either the beginning or the end of physical sciences. In his mind, it was the end, because he was really sure that actually natural history will just surpass of these materialistic theories that thinks that men are just mechanisms which are built like machines in that. And the second quote, actually, it's something that is very, very, very actual now, even if it was written in 1901. It was a quote by a paper of Pearson in Nature, and said that I believe that one day must come when the biologist will, without being a mathematician, not hesitate to use mathematical analysis when he requires it. So I think that now, as I was saying at the beginning, we are far beyond this. Biologists still have problems in using mathematics. So the one of you who try to publish in biology papers know that very well, because you get completely kicked out, not even without having a look at the paper sometimes. But it's changing. We have seen that if over the years this is more and more accepted. I think that we are much behind this, because now there will be a time where actually biology will just give us a number of more data that we can, more than we can actually process. And this doesn't mean that we need to resort to use data science or big data or whatever name you want this to do. It's just we are modelers. We have to use smart data. So we actually, there is a new place for mathematics in this. So actually there will be, I hope there will be a time where there will be a biologist that will be a mathematician, because actually in the biology we observe the world with the eyes of mathematics. So actually it's mathematics that actually will help to decipher biology. So there will be, I'm sure, a place for a new mathematics that will become by the development of physical or biological problems. Thank you for your attention.
Yeah. Okay. There is some complicated mathematics behind your equation, but the question is, the storage energy function elastic is non-convex, yes? In biological problem. Therefore, the number of solutions of elastic part of the problem vary in time, yes?
Yeah.
Therefore, you need some selection principle, which your equation should be supplemented with some selection principle, which choose the correct solution. Have you idea how this principle may be?
Well, actually, it's part of the slide that I have skipped, was like how this is deconvexified in that sense. Because even if you start with a material that is somehow convex, the fact that you change the matrix, it somehow changes your energy landscape in that way. Because you are changing the matrix, your matrix could not be Euclidean, so you could have something that naturally will have a Riemannian curvature. Then it means that somehow you have to end up with always with a minimization problem. And actually, it's not a trivial way of minimizing that, because remember, you also remember that we deal with energy functional, which not always are not convex, but which has nonlinear. We have derivative nonlinearities. So if you do like in terms of calculus of variation, you enter into a domain where it's very difficult to create. For example, what you have seen in faults. Faults are the exact paradigmatic example of a solution which you will never have it by using Weierstrass minimization problems. You have to find a good functional space which allows you to have this singular solution. So you have to resort to kind of quasi-convexity at the border. So it becomes a very, very tricky problem mathematically. But I still believe that chemical and mechanics, the chemical part will give a length scale, and the mechanics will give a shape. So they cooperate in that sense. So they give one each other information which are essential to create a global shape with a given size as well. But we can, I'm open to further discussion on this.
Yes, I can, because only remark, convexification leads to microstructure.
Yeah.
I think the discussion will continue
Okay.
in the break. So let's thank the speaker again. The next speaker, Iva Kanso. She'll speak about flow-mediated synchronization of swimmers and rotors at the micron scale.
Thank you so much, Shias, for the introduction. I'm not sure which one. Very good.
Best not to disturb the connector once it's.
Try this one. Let's try this one. Perfect. Good morning, everyone.